Hello, everyone, and welcome to Historical Geology 1404. Yay! Yay! Thank you, thank you, thank you. Oh, yes, thank you, thank you. Okay. How we feeling? Did you have a good 2-day break? Awesome. I didn't have a break, in case you're wondering. Thank you for asking. Okay, this is historical geology. That means a couple of things. Number one, you already know who I am because you took physical geology, either in an online class or in person with me, right? 1403 is a prerequisite to this class. I will reference things that we learned about in 1403. And yeah, the first couple of weeks here are mostly going to be review of 1403 because some of you took 1403 years ago, right? Yeah, I recognize you, right? So it's been a minute. So the first couple of weeks are going to be largely review, but I will be introducing a few concepts. And then in about week 3, that's when we really start diving into the new stuff, the meat of this class, okay? It's going to get fun. It's all going to be fun, but it'll get new and interesting at that point, okay? So I'm going to forego telling you about me because you already know me. However, you may not know each other. So I'm going to take a couple minutes. We're going to go around the room. You're going to say your name and your major and where you're from. Cool? Let's start over here.
My name is Elam. My major is STEM, and I'm from here.
Elam, STEM, you're from here.
My name is Mariana. I'm also a STEM major, and I'm also from here.
Also STEM.
My name is Jose, and I think I'm General Studies right now.
General Studies. And you're from here.
My name is Angel. I'm General Studies.
And you're not from here.
No,
I'm
I'm
just
from
kidding.
Cuba.
You're from Cuba.
Wait a second.
We'll take it.
My name is India. I'm from here. My major is STEM.
Yeah, so we're still keeping the STEM table going.
I'm Aaron Cario. I'm a STEM major. I'm from Augusta, Texas, not a place called here.
Not a place called here. Yeah, I get a lot of Hereians right now.
My name is Emily. I'm a business major, and I'm from Colorado.
And you're from Colorado. Out of curiosity, your jacket says Salt Life. What does that mean? You don't know? I know. I love salt, so maybe I should wear a jacket that says Salt Life. I'm living that salt life. I don't know what that means, but I like salt. Go for it. Okay, so undecided major. He will be a geologist.
My name is
Jocelyn, business major.
My name is Claudia. My major is business, and I'm from Mexico.
And Claudia, business, Mexico.
My name is Zara. My major is business, and I'm from Pakistan.
Zara, business, Pakistan. Cool. Yeah. All right, so now everyone knows each other. Out of curiosity, how many of you are high school students? Everyone this semester. Okay, I think Sebastian was the only non-high school student in our section last semester, wasn't he? No, he's not taking 1404. So see, high school students get absolutely zero choice, I think, in the classes that you take. And so they'll often sign you up for the sequence, 1403 and 1404, just one after the other. It's just easier that way. But when you're a grown student, you have minimal control over the classes you take. So they will automatically sign you up, but you can go to them and say, hey, I think I want to take this. It fulfills the same requirement, and I'm a little more interested in that. So I'll oftentimes get full-grown students who take 1403 and are like, oh, that was interesting, but now I think I want to try physics or biology for non-majors or something like that. And that's totally fine. It's up to them. But they'll miss out on what you're getting, and it's going to be fun. Okay, cool. So thank you for introducing yourselves. My online students who are watching this later, please feel free to do that exact same thing. Hopefully you did that in the comments as we were doing that here. If not, pause the video, do it now. Share something about yourself, who you are, what your major is. I will read through these later. The way that this works is you, my online students, will interact with this video. If you're watching this concurrently as I'm giving this lecture, it will be on GoReact. If you're watching this at a future time on YouTube, obviously you can use the comments if you'd like. I may or may not go in there. But on GoReact, I will be going in there. I'll be looking at your comments. I'll be responding. I'll be talking to you, answering your questions. If you want full credit for participating in this lecture on GoReact, you need to answer at least 3 questions that I ask during class, respond to at least 2 questions asked by other students, and ask at least 1 question of your own. Okay, if you can do those 6 things, you get full credit for participating in today's lecture, and that will be reflected on your grade. That's 20% of your grade. You don't want to miss out on that. For those of you here in the class, you get discussion boards. Now, in 1403, those discussion boards were largely, I give you some information, and you give me an answer. Or I ask you a simple question of your opinion on something. Largely philosophical sort of questions, right? And then you provide that opinion or an answer. In this class, all the discussion boards are research-based. I will say, here is a link to a website, for example. And on that website, you have a whole list of possible things that you could explore and research. I want you to pick a thing on a certain subject, explore it, read the article, give me a breakdown, tell me what you learned about that research. It's going a little bit deeper, okay? You need to check your sources, make sure that they are actual viable, trustworthy sources, all of that, okay? So that's what your discussion boards this semester are going to be. You're all already familiar with the labs, the way that I do labs. It is going to be somewhat different in this class, though. Most students say that the labs in 1404 are easier than the labs in 1403. You will not have mineral identification. There will be identification, okay? It's mostly going to be in the form of, here are some pictures, or here are some samples. For those of you that are in the classroom, you can see the physical samples. Tell me what it is. But I give you a catalog of possible fossils. It's impossible for me to teach you all the taxonomic classifications and how to tell all of these life forms apart from each other in the 8 weeks that we have for this class. So I give you the basics and then just ask you to basically match them, right? You know that a nautiloid has these properties. Okay, well now look at all of these pictures and this catalog I've given you, and then tell me which one is the nautiloid, right? Easier than 1403, but still works. So don't become lackadaisical, okay? Don't fall behind just because I told you it's a little easier, all right? You have exams in my class. Obviously, you're going to have a Module 1 exam, a Module 2 exam, a Module 3 exam, and a lab exam. Sound familiar? Right. It's the exact same format. I do, however, break apart the space between the exams a little different than they were in 1403. You had 4 weeks before your first exam in 1403, and then 2 weeks before exam 2, and then 2 weeks before the final. It's the opposite in this class. In 2 weeks, you will get your first exam. 2 weeks after that will be your second exam. 4 weeks after that will be your final. Okay, so just keep that timeline in mind. If at any point you notice that my due dates seem to be a little bit off that I put on the syllabus, just know that it's because I was in a hurry when I made it. Okay, so I am human. I could have made a mistake. Just ask me, Mr. Hart, is that accurate? You know, is this actually the correct due date? And I'll either say yes and I'll say no. If I say yes, we're standing by that due date. If I say, no, sorry, I will fix it, then thank you for bringing that to my attention. Please don't hesitate to ask questions. Y'all have taken a class with me before. How serious am I about asking questions? As many as you can. How many times do I ask you for questions? How many times do I beg you for questions? Right? If you're not asking questions, you're not really learning, right? It's a huge gauge that I use to tell if you are actually learning something by the questions you ask. The fact that you are asking questions means that you're listening to what I say and trying to process it. Not asking questions, I don't know if that means you're just a super genius who immediately gets it, or you're not paying attention at all. Okay? But your grades will reflect that in the end. So please ask questions. And again, for those of you watching this on GoReact, you ask your questions on GoReact, and I will respond to them there. Let's see. Notes. How serious am I about notes? Really serious. And it's extra credit, right? You get multiple bonuses for taking good notes, right? First of all, they are worth extra credit. 50 points of it. If you turn in all of your notes by the end of the semester, I throw 50 points on your lowest exam, which is significant because 2 of your exams are worth 100 points, right? That's half an exam. That's how serious I am about good notes. If you don't take good notes, you won't do well, okay? And I let you use those notes on exams. You can use them on exams. So not only do you get better grades by having good notes because your notes are good and helping you on your exams, but I also throw extra credit on top of your exams because you took those notes in the first place. Win-win, right? That's a win-win for you and a win for me because you succeed. So it's a win-win-win, right? Love it. Great. Let's do it. Good notes. If at any point you realize, these notes are a little weak, feel free to ask me questions, okay? Oh, that brings up another good point. Do not, this is very true for my online students more than anything, do not use the Blackboard messaging service. What do I mean by that? Here's our class shell. Do not do this. That right there, that's the devil. Stay away from it. Okay? None of that. Why? Because it does not tell me if you send me something there. I don't get a notification. So your message could sit there for days before I notice that there's a little pop-up there that says, someone sent you a message on Blackboard, right? And if it's over the weekend, I ain't going to see it. Because guess what? I'm not on Blackboard on the weekend. Okay? I'll go on Blackboard on Monday, and I may see it then. The best way to contact me, email. jhardt@odessa.edu. That's my email. That's how you should contact me. That is the most reliable way. I instantly get that message, and if I have the time at that moment, I usually respond right then, right? I don't know how many of you all sent me emails last semester. How many of you sent me an email and then got a message in like 10 minutes? I do that a lot. I'm not going to lie, most of the time it's my online students that send me emails. You guys usually wait to ask me questions or whatever when we're in class. But I do it immediately if I can, by the end of the day if I can't. At the very most, if you send me an email on like Friday evening, I've already left work, I'll answer it on Monday when I come back to work. Sometimes I even answer emails on the weekend. It just depends on what I'm doing with my family, okay? But email is the best way to get a hold of me. What else? Please, no cheating, no plagiarism, especially when you are doing research exercises, right? Like you are doing in this class this semester. Be very careful that you cite your sources. I encourage group work for lab activities, and yes, even for discussion boards if you would like to, okay? But no group work on exams. None of that. If any of my online students would like to form a group to work on an assignment together, you can coordinate that with each other on GoReact, and then one of you can send me an email with the list of people who want to be in your group, and I can actually make a private discussion board for you and your group, just the people in your group on Blackboard, Okay, so I can do that, but I need one person in your group to tell me who is in that group first. Okay, so coordinate that with each other on Go React, just right here in the thread on this or future videos if you would like. Alrighty. I think that's all the logistical stuff I can think of. Any questions? Did I miss anything? Licking rocks is entirely up to your prerogative, my friend. Always has been. You just didn't know it. You're free now. Okay? Lick all the rocks you want. Disclaimer, I take no responsibility for any health issues that are a result of that. Samples 18 and 37 are not marked in nature, right? You what? You licked like 20 rocks? Uh-huh. Mm-hmm. Mm-hmm. Chalk? Was it real chalk?
Yeah.
Okay. Good. Okay. Anything else? No? We're clear? We're good? We're ready? All right. Let's begin. All right, so today we are discussing Earth as a system. And like I said, this is going to be very familiar to any of you that just took 1403. But we're just going to kind of breeze through this, okay? I'm going through what in 1403 we took weeks to cover. I'm going to go over in a lecture today, okay? So just summaries, okay? I haven't updated this first slide in a year. So this is last year's picture of my kids. A lot of you have met him. Yeah, that was my son at the movie night. Yeah, he's 6 now. He's 4 in this picture. And she is going to be 4 next month. She's 2 in this picture. And he was about 4 or 5 months in this picture, and he just turned 2. Yep. Okay, there's my email. You're already familiar with all that. Yep, all this. Okay, so I want to start off with a quote from Charles Darwin, who, believe it or not, is going to be, he and his work and the results of his work are going to be a big factor in our class, okay? It is interesting to contemplate a tangled bank, clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other and dependent upon each other, in so complex a manner have been produced by laws acting around us. We learned about some of these laws in 1403. Laws of nature, if you want to call them that. Okay? Some things that we just naturally assume are fact. Gravity makes things fall. Friction heats things up. Water moves downhill, right? But all of these laws, as we call them, act together in our universe to generate complex cycles and spheres and just everything being intertwined to make things the way that they are right now. Okay? It is these laws of nature that make every insect, that make every planet, that make every galaxy, that make every blade of grass, that make every one of you function. Your body, is made of trillions of cells, all of which are working together for one common cause: to keep you alive. Every cell, a unique organism that have all learned how to coexist. How amazing is that? You are a microcosm of the planet. All of the things on this planet all working together to make this planet. and in fact, a smaller representation of the galaxy and the universe, dictated by these laws. We're doing big brain ideas in my classroom, right? Okay. So why is it important to study all of these things? Why study geology at all? Well, a couple reasons. First of all, we see a thing and we want to know what that thing is. We want to understand it. We try and make sense of it, right? That's what we do. If I were to do this, you'd be like, Mr. Hart, why'd you knock over your water bottle? That's your water bottle. It wasn't even Angel's water bottle. Why would I knock it over, right? You want to know? Well, I'll tell you to make a point, okay? But we see a thing and we want to understand it. We want to know why. What is the why? What is the what? What is the who? Okay? That's just something that is second nature to us. Actually, I wouldn't say it's second. It's primary nature to us. Okay? Everybody does it. So we want to understand why mountains form, why glaciers form, why. That's the first reason. The next reason, we want to try, through that understanding, we want to try and predict or forecast, whatever word you want to use, the future, if you will. Our future, individually, would be nice. I want to know what my future has, and so I try and build my life in such a way that I can predict where it will end up. Very hard to do that, by the way. Y'all are still very young. You'll understand plans don't always pan out, and sometimes opportunities come out of nowhere and you got to grab them, right? But the future of human civilization, okay? The future of our planet. What is the fate of our planet? How many of you can tell me? Can anyone tell me what the eventual fate of our planet is? Ah, death. And now things get dark. No. Well, maybe a little bit. Okay? Things, we're going to be talking about things in here that are going to make you wonder, is Mr. Hart a nihilist? But I promise I'm not. I'm just spitting the facts, okay? Eventually, our star, which we call the sun, its real name is actually, do you remember what the real name is? Sol, thank you, which is why we call this the solar system. There is only one solar system because there's only one star named Sol, right? So our Sol, our star, is going to go through an end phase, okay? Right now, it is burning its way through hydrogen and some helium and calcium and all of this stuff, sodium, okay? Right now, it is putting out what wavelength of light? Do y'all know? What color is the sunlight? Huh? White? Invisible? Okay, I heard someone say yellow. The sun, is it yellow? No. What color is it? It's white. How do we know that the sun's light is white? Because snow is white, right? Unless you're stepping in the wrong snow. But it should be white, right? Snow reflects the light wavelength of the light from our sun. The snow is white, therefore the sun's light is white. Why does it sometimes appear yellow to us? Why do we always draw the sun as yellow? Because what our eyes are picking up, those wavelengths, are making it through atmosphere, and it's getting a little diluted, so to speak. Okay, but the light that the sun is putting out is white. We have a star that is, let's say it's about middle of the road. It's not too big, it's not too small. It's that Goldilocks just right, if you will, okay? Which means that its fate is probably not going to end on an explosion, a nova. You've probably heard that term before. Some stars blow up. Those tend to be the supermassive stars. They collapse in on themselves, make that explosion, and go nova. Our star's eventual fate is going to be turning into what we call a red giant. It is going to expand outward as it starts burning or fusing and pulling apart heavier elements. It's going to expand outward. It's going to cool off. But as it expands outward, it's going to swallow Mercury and then Venus, and then Earth. Cooling off and expanding, and even though it's cooling off, it's still going to be hot enough that it will burn Earth to a crisp. That is the most likely fate of Earth. But don't worry, it's about 5 billion years away. Okay? All things come to an end is my point. Trying to understand the future is another big aspect of why you study geology. Will we end up in another supercontinent? Many people believe so. That supercontinent has a really dumb name called Neopangea. I hope we rename it before then. But yeah, that's part of the future that we can explore theoretically by studying geology. And then also, our civilization relies upon materials. Materials that come from where? The Earth. Everything that we use to produce comes from the Earth. The salad you eat comes from the Earth and is grown with minerals. The wood that your desks are made out of, grown with minerals, harvested from the Earth, using tools made of metal and plastic and probably other wood as well. Metal and plastic both made from the Earth. Metal by smelting it out of ore. Plastic is mostly made from the byproduct of refining petroleum. Next time you hear someone say, shut down the oil industry, we need to stop burning fossil fuels. I understand that, and I do agree that we need to back off from fossil fuels. I'm an environmental guy, right? My whole thing is policy and trying to find regulation and middle ground and compromise and all of that, right? We do need to back off of fossil fuels eventually, but if we just turn off the tap right now, what happens? Not only do all our cars stop running, we also turn off the tap on making things like plastic. Can you imagine your world without plastic right now? Look at the laptops in front of you. Look at your phones. Look at your shoes. There is plastic in pretty much everything. Now, before entirely turning off that tap, there have to be some other decisions made. Primarily, where does our energy come from after the fossil fuels are not being used anymore? But also, what do we start using instead of plastic? Do you know what we used for all of this stuff before we started using plastic? Say that again? Rubber. Rubber and plastic come from similar sources. From the oil industry is a primary source. Wood. Are you willing to start chopping down way more trees to replace the plastic that we can no longer produce because we no longer generate fossil fuels? Or use fossil fuels, I should say? It's the devil's catch, isn't it? How do you decide? And that is why these decisions have to be made with thought. Okay? But regardless, right now, our civilization still relies upon materials like petroleum. Okay? And yes, lots and lots of metal. We chew through tons and tons of metal all the time, every day. That metal comes from the ground. You need geologists to figure out where these resources are. So there are many reasons why studying geology is important. By the way, another important resource, water. So much of our fresh water comes from underground, right? Okay. Remind me what dynamic Earth means. Anything to add? True. Echoes of each other. Fact. The Earth is always changing. There is always some kind of activity going on. It is never, ever at a point where it's just, there's something not happening right there, right? In this environment, in this classroom, this rock has been sitting for who knows how long. Actually, I put it there about 4 years ago. Before then, it was in that prep room, and I have no idea how many decades it was sitting in there. But even in this classroom, this controlled environment, something is happening to that rock. Some chemical reaction to the oxygen in the atmosphere, Maybe if I accidentally sprayed it one time with cleaning solution during COVID, right? Maybe that had a reaction. There is something always happening, okay? So, and then in an uncontrolled environment, by the way, not in a classroom where, you've got air conditioning and there's not going to be the threat of things falling on top of it. Out there in the wild world, so to speak, how much more dynamic is that, right? Very. Where rainfall happens, where wind is constantly moving. There are landslides and earthquakes and volcanoes, all of these examples of how dynamic Earth is. But also there's those small things like that chemical weathering, right? The things you and I may not notice is happening. The process by which sediment becomes rock. Do you remember what that's called? Sediment becoming sedimentary rock, that happens through lithification, right? Okay. All of these examples of how dynamic Earth is. And it is all of these dynamic events that eventually lead up to the big changes, the big features that we see. Okay? You can get Grand Canyons from the simple effect of water. Running water. Why is it running? I don't know. You better go catch it. But you got this running water, and it's making its way through the rock, and it's carving and cutting its way down until eventually you end up with something as incredible as the Grand Canyon. Okay? Or on those tiny scales, a fossil, where each cell is replaced by a single crystal of a mineral, maintaining the shape, even some of the soft tissues potentially, like the feathers in this Archaeopteryx. Okay? All of this example of dynamic Earth. Let's review the history of science for a moment here. You may recall from 1403 that scientists were not always scientists. We refer to those early people who started asking questions and attempting to answer questions. We tend to think of them more as natural philosophers, okay? They asked and answered these questions based upon what they could see and their intuitive answers or their knowledge of the time, okay? Not terribly dissimilar to science at its fundamental level, except that science includes experimentation, okay? So, gentlemen like Aristotle, ask questions, answer questions, and he would give answers very similar to, the gods did this. But also, trying to reason it out. If there's a fish fossil in a rock, then it must be because fish live in rocks, right? It wasn't always just, the gods did that, right? He tried to reason it out with the best reasoning that he could. He had no concept of how old the Earth was, could not even begin to, at least as far as we know, begin to comprehend the process of lithification or anything like that. He answered things the best that he could. But the process of asking and answering those questions was important. And these natural philosophers did that. Okay? That lasted for a long time. Christianity comes around, right? And you have the Bible. The Bible includes dates, times. And so James Ussher here took all those dates and times, calculated them backward, and came down to the date that the Earth was made October 22nd, 4004 BC. Someone tell me what date it is right now. What's the date today? October 17th. So we have in 5 days. What will it be in 5 days? What day is it? October 22nd. And what day is it? What day is it? Tuesday. Thank you. Guess what? We're having class on October 22nd. We should have cake. We should have Creation of the earth cake. I'm not trying to be sarcastic about anyone's religion here. I just think that it's funny that October 22nd somehow is the date he came down to. 4004 BC, sure. Math, fine. October 22nd, not sure where that came from, but it falls on a class day. So if anyone wants to bring some fun, yay, let's celebrate Creation Day or whatever snack, we can do that. I might bring something. I might make something. It could be fun. Okay, so this caught on very well because in the 1600s, Christianity was going with all of those conquering, colonizing empires all over the planet, right? France and Portugal and Spain and Italy and England in particular, right? Taking Christianity and this newly formulated date of creation with it. And so that's why so many Christian denominations around the world hold that the earth is about 6,000 years old. That's where this comes from. Okay? Now, if you hold the Bible to be the one and only true document and to be completely literal, that's entirely up to you. He did, and that's where he got this conclusion, treating the Bible as a completely literal historical document. I need to put out a little caveat out there. Y'all may remember when I said this in 1403. It's even more true now. Nothing we discuss in this class is meant to persuade you or dissuade you to or from any of your personally held beliefs. If this is something you believe, I will not attempt to persuade you otherwise. I will, however, give you alternate hypotheses based upon scientific conclusion. Okay? We will be discussing evolution at length in this class. I apologize if that disturbs any of you who have other viewpoints. If you would like to discuss religion and evolution and all of those things, I am happy to have that conversation with you. I have found my own resolution for the two, and that's something that I'm happy to discuss with you outside of class time. When I end the recording, when we actually stop the discussion, at that point, we can have such a conversation, but it's not appropriate to have that conversation during class time. All right? More than happy to have that conversation with you afterward, as a group or individuals in my office. Okay? All right. So, along with this came the belief called catastrophism, that these large features like Grand Canyons and trenches and mountains and volcanoes and all of these things were formed in incredibly cataclysmic, catastrophic events. A mountain can be raised in a few days. Volcanoes form in a few days. Canyons carved in a few weeks by massive flooding events. All of that. Catastrophism kind of explained away all the big stuff. Okay? That only lasted for so long, though, because eventually people started to ask, okay, well, where is the big stuff now? Why aren't we seeing any of this big stuff make big stuff? Right? These big events, why isn't it making more mountains where we can see it? Right? We see volcanoes erupting, but there isn't like some massive eruption that makes a volcano in a matter of days, right? So catastrophism started to be questioned. Now, one of the guys who was starting to ask these questions about all of these belief systems that had been in place for a long time was James Hutton. And Hutton did that vital first step of actually bothering to collect evidence. Okay? Matter of fact, it took him years. He spent decades collecting data about Earth processes to try and figure out a few important things, like how old the Earth is. It is James Hutton who came up with the principle of uniformitarianism, which you may read some literature called actualism. Okay? Principle of uniformitarianism. Physical, chemical, and biological properties, biological laws that operate today also operated in the geologic past, right? That was the conclusion. He's not the only person to have come up with this idea, by the way. This particular phrasing is his, and it's my favorite phrasing of it. Okay, but this idea had been around for a little bit before him. Okay, it's very important to recognize that the things that we observe today, those aren't new. They've always happened. And why? Because they are the product of natural laws. And how long have those natural laws existed? Forever. As long as the universe has been around, these natural laws have been around, right? It's nothing new. And therefore, the processes that we observe today are the same processes that have always occurred. Using that logic, you can say it takes this long for a thing to happen now, which means that it took that long for that thing to happen before. And then you can kind of work backwards, right, and figure out approximate dates for things. Now, he came down to a date of the Earth that flew in the face of Christianity. I believe his was somewhere around the 210 million year mark. Based on his observations, the data he collected, he believed the Earth was about 200 and something million years old. Okay, which obviously we know is nowhere near as old as it is now. But back then, when everyone was saying 6,000 years, they laughed him out of the room until his enormous quantity of collected data was published and went everywhere. And all these scientists were like, oh, he may have a point. Eesh, this is awkward, right? And it was awkward for some people. Anyone who stood in the face of the large Christian denominations historically didn't turn out well for them. Worst case scenario, house arrest. Or best case scenario, house arrest, I should say. Worst case scenario, many people who doubted were poisoned or executed. Yep. Okay, so you remember the exercise we did about how old the Earth is, right? I'm going to skip through this because y'all may remember this. How big is a billion? You remember this sheet? Yeah? Do you remember how many dots were on that sheet? Not 1,000. Not 3,000. I mean, yes, it does say on the other slide. It's not a billion. 4,000. Yes, you were closer. There are 4,000 dots on that sheet. Here's one of those sheets, right? So if I want 1,000,000 dots, how many sheets of paper do I need? $250 sheets. Here's a ream of paper containing 500 sheets. Is this all coming back to you now? Okay. So how many sheets of paper do I need to reach 1,000,000,000 dots? Just add 3 zeros, right? So if we needed 250 sheets to reach 1,000,000, how many to reach 1,000,000,000? 250,000 sheets. That's 500 reams of paper. That's a tower of paper, 83 feet. That's an 8-story building, just under 8 stories. Okay? To reach 4.5 billion, that would make tower paper 380 feet tall. Have any of you stood on a 38-story building? No? You would remember. Yeah. Like looking down, the people, they're like ant-sized. They're tiny, right? Actually, even smaller than that. But yeah, it's something you would remember. That's a lot of paper. Each sheet of paper has 4,000 dots, and each dot represents 1 year of Earth history. Okay? Earth is very old. If you wanted to put this in other terms, we could go for a walk around the equator. Based on the average human step length, you would have to go around 15 times to reach 1 billion and 70 times to reach 4.5 billion. So how do we know how old the Earth is? The moon. Okay, we'll come back to that. How do we know through the moon? Huh? You what? We just don't know? We're guessing is what you're saying? Well, we're not guessing. The law of superposition. What is the law of superposition? Whatever is on top is younger. So, on the bottom is the oldest, on the top is the youngest, right? This is a cross section of the Grand Canyon, by the way. Okay. I'm going to put these two objects down. If I put them down at the same time, they will be side by side, correct? If I want them on top of each other, if I want to stack them, one of them has to be put down first. Which one was there the longest? The ream of paper. That's the law of superposition. Okay, so how does this help us? It provides us relative dating information. Okay. Every time I use the term relative dating, I remember this guy in my class a few years ago who made a joke about dating his cousin. Yeah, great, right? So, relative dating information is basically talking about this is older than this, is older than this, is older than this. The fact that they're stacked tells us how old they are relative to each other. Now, while that doesn't give us an actual date, it is very helpful if I'm in the field and I can say, okay, just looking at the layers of rock up there, the fact that this limestone is under the sandstone, and I'm looking at all these chunks of rock scattered down here in the bottom, like that's limestone, that's sandstone, this is older than that. And if I find fossils in those two chunks, that helps me, okay? Fossils takes me to the next method, index fossil succession. Remind me what an index fossil is. We covered this briefly. Believe me, we will talk about it more in this class. Can anyone remind me what an index fossil is, though? Well, that's fossil succession. The law of fossil succession basically is if I have layers of rock that all contain fossils, and I go and find these layers of rock at different locations, I can always be sure by finding those fossils which layer of rock I'm in, right? If layer A has these two fossils, no matter which location I'm at, if I find layer A, I know I'm in that same time zone, right? Same thing for all these other layers. However, if we add a small little element on top of that and say index fossils are those which have a few distinct characteristics that live for a short period of time. The shorter the period of time that we can confirm they're in the fossil record, the smaller the area, the vertical area that we can correlate is. And that's very useful for a number of reasons, which we will talk about later in the class. And the third method of dating, radiometric dating. What is radiometric dating? It does have everything to do with radiation. Well, radiation, I shouldn't say everything. Radiation is a byproduct of what we are talking about. Okay. I don't need to go through all this again. This is an example of the law of superposition. A is older than B, is older than C, is older than D, is older than E. And then for a fossil, by the way, the definition of a fossil, one of the definitions of a fossil is that it needs to be over 10,000 years old. Okay? Anything younger than 10,000 years old, and that we tend to hand that over to an archaeologist. So a lot of you are familiar with the fact that I've done paleontology. If there is a branch of geology that I am, other than being a geologist, I'm a paleontologist, right? Paleontology, we like to take the things that are older than 10,000 years. An archaeologist will often hand us the thing if it's older than 10,000 years. If I find something that's younger than that, I'll hand it to them. It more than likely has something to do with human history more than it does with just natural history, which is my domain. Okay? Now, there are exceptions to that rule. If there's absolutely no way that had anything to do with human history, they may give it to me anyway. And if I find something that's older than 10,000 years old that has to do with human history, I will hand it to them because that's their specialty, right? But for the most part, 10,000 years, that's that cutoff. Fossils include bones, plants, trace fossils, evidence of life without actually being a piece of that life itself, things like that. I've shown you some of these pictures. That's a turtle shell I found in Montana. Those are some fossilized tree trunks, some of which I've got here. These are giant snails. These were about the size of my fist. I found these in Texas about a decade back when I was driving across Texas here. I actually still have these. I thought I had one out here. I might have them in the back room, but yeah, they're about the size of my hand. Index fossils. Okay, here you got different fossils. You can use these fossils to tell the ages of rock or the relative ages of rock across distance, right? Whether you're 100 miles away or 1,000, if that fossil is present in both layers of rock, they are the same age, right? Requirements for being a good index fossil: it needs to have been alive for a short amount of time. There needs to have been a lot of it because let's say only 1 in every million individuals gets fossilized. I need to have a lot of those things living for there to be enough fossils that I can find them, right? So there has to have been a lot of these things. Widespread habitat. It doesn't do us any good if they only lived in a single lake in the middle of Oregon, right? The larger the area, the habitat that these things live in, the more we can use them to correlate in more places, okay? And then finally, they need to be unique. They need to have a unique physiology. While you can tell that all of these organisms belong to the same group of animals, or whatever these are called caimanolecules. These are invented organisms. These don't actually exist. This is actually an exercise that I did when I took this class more than a decade ago. These are called caimanolecules. We cut these things out, and then we had to put them in their evolutionary order based upon inherited traits. I'm not doing anything that difficult for you in this class. We're going to do similar sort of things, though, okay? Or have similar discussions at the least, okay? But you can tell that they all belong to the same general group of organism, but they all have unique enough characteristics that I can easily tell them apart from each other. That is essential for an index fossil. Because if I have 2 species that are nearly identical to each other, I'm going to get confused between them all the time. That's not very effective as an index fossil, right? Examples of good index fossils: ammonites, brachiopods, very commonly used index fossils. We will talk about both these organisms. Now let's go back to radiometric dating. Okay? This uses isotopes. Remind me what an isotope is. Don't look. I'm not tall enough, am I? Yeah. Okay, wait. That's going to work, right? All right. Remind me what an isotope is.
When an element is missing an electron.
It's missing a what?
An electron.
Not an electron. Try again.
Proton.
It's not a proton.
Atom.
It's not. Are you mocking me? I'm just kidding. All right. It's missing a neutron. Thank you. Okay. He was playing with me. If it's missing an electron, what do we call it? If it's missing or gained an electron, it becomes an ion, yes. An ion, not an anion. That's a different, it's part of it. It's a kind of ion, but we're not going to go that deep into it, okay? It becomes an ion if it gains or loses an electron. Why? Because its charge changes, because electrons are negatively charged, right? If we gain or lose a proton, it becomes a Different element, because the number of protons in the nucleus determines the element we're looking at. If it gains or loses a neutron, it becomes crazy. Yes, no, it becomes an isotope. Okay? Now, you can have stable and unstable isotopes. Stable ones are ones that really don't care if they have an extra neutron or two. There are stable carbon isotopes. There are stable oxygen isotopes, right? And we use the ratios of those all the time, okay? Carbons 12, 13, and 14. 12 is your basic plain Jane carbon, right? Carbon 13 has an extra neutron. Carbon 14 has how many? 2 extra neutrons, right? Now, unstable isotopes. Let's talk about uranium. What do we use uranium for? Not batteries. Yet, anyway. Energy from how? Yep, you can make bombs out of them, but energy how?
You can make a water near it boil and turn it to steam, and then you can turn motors.
You are describing a nuclear reactor, sir. So you can make a nuclear reactor with fissile material, that is material that's falling apart at the atomic level, okay? And, yeah. Yes, exactly. It is, as it's falling apart, it is expelling radiation. This is why it is called an unstable isotope. It does not like the fact that its mass has changed. I know I'm anthropomorphizing a little there, but follow along. It doesn't think anything. This is one of those natural laws. It's a consequence. It gets extra or loses isotopes or neutrons, which, by the way, how many neutrons did we lose while going from 238 to 235? 3. All it took was losing 3 neutrons, and it's falling apart, literally. As it's falling apart, trying to find a new stable condition, it's going to blast electrons and protons and neutrons and electron, proton, and neutron pairs. It's going to be blasting off simple particles that may eventually become hydrogen. It's going to be blasting off nuclei that go on to join other things and become. So it's blasting off all these different kinds of radiation, all these particles that we call radiation, until finally it reaches a new stable state. In the case of uranium, it will become lead-207. Okay, but it takes a long time for that to happen. We can take advantage of all that radiation blasting off of this unstable isotope to heat up things like water, like you were saying. When you heat up that water, it becomes steam. What can we use that steam for? What have we used steam for hundreds of years? Huh? What? Heating? How do we use it for energy? How do you get the energy from the steam? You ever seen a steam-powered engine? Steam turns a turbine. Now, we've kind of progressed a little from those initial steam engines where the steam itself would turn a turbine and that turbine would turn wheels. Now we've kind of graduated a little bit. We put magnets on those turbines. And if you spin those turbines with those magnets fast enough, you generate an electrical charge between the magnets. And that electricity gets transferred down the lines and powers homes and businesses and anything nearby that is connected to it. Okay, that's how a nuclear reactor works. Fissile material generates radiation, turns water to steam. Steam turns a turbine, turbine turns a magnet, magnet makes electricity, electricity goes to power things. Okay, that's a nuclear reactor in a nutshell. Okay, now, while that's cool, we can also use radioactive unstable isotopes for another reason, in another scenario. Okay, they go through something which we call a half-life. Okay, A half-life is the amount of time that it takes for half of the mass of an unstable isotope to decay into its stable daughter isotope, okay? So half of the material. A half-life is how long it takes for half the material to decay. So let's say I have a dinner plate full of yummy, delicious uranium-235. Right? I know that looks like a cookie. It keeps coming up. Okay, fine. This is a uranium. You twisted my arm. This is a uranium cookie, okay? I know. Isn't that sound awesome? Something like the Hulk would eat that. Okay, so each one of these dots represents some quantity of uranium. After one half-life, how much of my uranium will have decayed? Half of it. Half of my uranium is now lead after one half-life. In the case of uranium-235, that takes about 703 million years. So, practical question. Here's a scenario for you. If I do an isotope analysis on a rock and I find that the ratio of uranium-235 to lead-207 is 50% to 50%, how old is that rock? 703 million years old, isn't it? Yeah. This is how we use radiometric dating. By the way, you've probably heard the term carbon dating before. That only has to do with carbon, okay? The ratio of carbon-14 in an object, okay? That only goes so far. Normally, after about 50,000 years, it gets really inaccurate. So, yeah. So we only use that for short periods of time. Anything older than that, we require radiometric isotope dating. Like this, you can use uranium, thorium, potassium. There are lots of unstable isotopes that we can use for this process, okay? So, after one half-life, you'll have 703 million years. Let's have a little exercise, right? If I have 500,000 parts per million of lead and 500,000 parts per million of uranium-235, it's one half-life. How much of each would I have after two half-lives? 250,000 parts per million of uranium-235 and 750,000 parts per million of lead-207. That's two half-lives, which means that now we're looking at about 1.4 billion years old, aren't we? How about in the half-life after that? 125,000 parts per million of uranium-235. 875,000 parts per million. I sound like an auctioneer. 875,000 parts per million and 125,000 parts per million, right? And then after the half-life after that, and then after that, and then after that, and after that, how many times can you divide something in half before you run out of it? Infinite, right? That's why we use half-lives, because it is a method of dating these objects that literally doesn't have a limit, okay? Make sense? Cool, cool, cool. So how do we use this? Okay, well, we know that the Earth is about 4.3 billion years old because of a rock that we found in the Jack Hills in Australia, okay? It's actually a crystal. This is the crystal. That is a 4.3 billion year old crystal. But the Earth is 4.543 billion years old. How do we know that? Aaron? You were saying this earlier? Because of the moon. The oldest moon rock that we have brought back to Earth is 4.543 billion years old. The moon was made, we believe, when another planet called Theia crashed into primordial Earth as both were still cooling and basically restarted the whole cooling process. A whole bunch of debris was blasted off into space, circled our planet, caught in our orbit, gradually coalesced into the moon. Now, there are a lot of things about the moon and about this whole thing that are quite fascinating. Sorry, I'm going to go off on a few very interesting tangents here for a minute. We thought that the moon cooled off really quick after this. It's small. The Earth is, or the moon, I should say, is very small. I want to say it's about 1/50th the mass of the Earth. Okay? But it's also very large compared to other moons in our solar system. I'm going to say, is it the 8th largest? And one of the only truly rocky ones. Okay? Which makes it very unique in our solar system. We believe it cooled off very quickly. We assumed that it cooled off probably about maybe a couple 100 million years after it formed because it's so small. However, the Chang'e 5, I want to say it was, reconnaissance drone sent to the moon by China returned last year with a rock sample from a lava flow on the moon that was only 2 billion years old. There was active volcanism on the surface of the moon 2 billion years ago. Now, that's before anything more complex than bacteria was growing on our planet, right? There wasn't like there was anything that was looking up at the sky going, huh, there's a volcano on the moon, right? But that's still, it lasted a lot longer than we thought it would have. And there's lots of fascinating conversations debating as to why that is. Probably has something to do with gravity from Earth, the gravitational pull from Earth, and maybe even the gravitational pull from the sun at different times, kind of warping the core, kind of flexing the core of the moon, pulling it this way and then that way and this way and that way, keeping some heat alive from friction in the core of the moon until it died. But it's still fascinating to think that we had a volcanically active moon 2 billion years ago, isn't it? Maybe that's just the inner nerd in me. I've always been fascinated with the moon. There was something else really interesting. Oh yeah, the collision of Theia with Earth. Can any of you positively tell me, 100% identify to me, that the Earth had everything it needed for life before this collision? No, I can't confirm that. Maybe we had just the smallest little bit of carbon. Maybe we had next to no phosphorus, right? Both of which are essential for life as we know it. Maybe there wasn't enough of all that stuff on Earth until Theia hit us. Maybe for however long Earth existed before this collision, it was as much a lifeless orb as Venus or Mars. Lifeless, we think. We'll see. Okay? And then Theia hits us. Heck, maybe life had already started on Theia. And then it hits us. And the two masses collide. They mix ingredients up. And everything that we need for life to begin is now here. How interesting would it be to think that our primordial ancestors could have started on another world? As a matter of fact, excuse me. Matter of fact, this is a subject that we will delve quite deeply into later on, called panspermia. We will discuss that later on in the semester. Okay. So, how do we do science? The scientific method. Can you remember the scientific method? How about we utilize the scientific method together? I don't think I did this with y'all in 1403, did I? I am going to be handing some objects. Come on, camera, stay with me here. some objects out to the class. I'm going to give you a picture here. I want you to describe these objects using general terminology. Tell me about shape, features, anything that you see. Okay? We're going to make a list on the board. We are collecting data so that we may eventually form a conclusion about what this object is, and maybe, just maybe, its purpose. Yeah. I will need these back, by the way. No one's going golfing after class. Golfing, what's that? Okay. Let's make a list. I'll just do it right here. Object, because we don't know what it is. What do we see? Describe. It's round. Is it round? Round is a two-dimensional shape, isn't it? Spherical, that's three-dimensional, okay? Spherical. Good. What else? It has dimples, okay. It's got those kind of weird dimples in it. Good.
Tailor-made.
Huh?
Tailor-made.
Tailor-made. We don't know what that means, but it has words on it, right? It has some form of words on it. It has words. What else? It has what? Distance. Oh, as another word? Okay, well, it has words. Analyzing the words is something we can do later. Right now, we're collecting data about the object itself. It has words. That is something about it. Yeah. Okay, it has a white color. Okay, let's talk about the weight. Does it feel heavier than it should for its size? Lighter than it should for its size? A little heavier? Okay. It is heavy versus volume. Okay, so it's probably got some density. Okay, well, we'd have to test the material to figure out what it's made out of. Is there anything we can do to this thing right now to try and determine what it's made out of without going too deep into the testing? Okay, so you could say scratch it on glass like we did with minerals in 1403, right? There are some things, but we're not quite to the testing phase yet. I want observations, not direct tests. What was that? It bounces. What else? How easily does it roll, Jocelyn? It rolls, but it's spherical, so that makes sense. But how easily does it roll? Is it a perfect sphere? Okay. What might be inhibiting its rolling? The dimples. Okay, so let's edit this a little bit. Not easy roll. What other observations? We feel like we've covered it pretty well? Yeah. Okay, so the dimples are evenly spaced. I like it. And evenly spaced. My purple pen is running out of ink, I think. Anything else before we move on to the next phase? What's the next phase, by the way, of the scientific method? Make a hypothesis. Okay, so using the data we've collected, give me a hypothesis. Ignore any preconceived notions you have about this object and give me a hypothesis based on what we have collected here. We'll use a different color for our hypothesis. Spit them out. What do we got? Okay, so it's not ideal for rolling a long distance. That's an observation, okay? Not good for long distance rolling, okay? And that's connected to our thing up there, but it is an observation. Give me a hypothesis for what this thing is based upon this data. Huh? Okay. It could be used for a sport of some kind. Balls have been known to be used in sports, right? Historically. What kind of sport would need a ball like this? I mean, what can we determine about this thing based upon its characteristics? It's not good at rolling. It's brightly colored, huh? Why would it need to go through the air? Okay, now we can test that, but first we need a hypothesis. Your hypothesis is that it may fly through the air better because of the dimples. Okay, so first hypothesis, ball. It is a ball meant to, it's an M, to fly through air. Green may not have been the best choice here, but I'm saying it as I write it. Okay. What other objects may be intended to fly through the air at great speed? We've already covered the ball. What other objects may be intended to fly through the air at great speed? It's a bird, it's a plane, it's a frisbee. No, it's Superman. No. It's clearly not any of those things, right? What if it's intended to be a weapon of some kind? Flying through the air at great speeds, a lot of weapons do that. Could it be a weapon? As far as we know, it could. That is also a possible hypothesis. It is intended to do harm. There is nothing on this list of observations that can disprove that. What else? Any other hypotheses before we move on to testing? All right, what tests could we conduct to figure out whether it is a ball or a weapon? Okay, well, you could chuck it at someone. It would probably be effective at either. However, what is it ideally used for? What is its actual purpose? That's what we're trying to figure out. So, how would we be able to test whether it's good at flying through the air? Because that's only a hypothesis. Yes, aerodynamics test. Launch the sucker, right? Chuck it. Give it a certain amount of newtons of force, maybe a scale of newtons of force, right? Start with a certain bit and then work your way up and determine, is it more or less efficient at flying through the air than a ball of similar density, similar size? We can do a composition test, maybe similar composition, but without the dimples. Would it fly further? Would it fly less? What we would find if we did that is, let me grab my red pen here. What we would find is that it does, in fact, fly further than non-dimples, than any ball of the same size and composition that does not have dimples. Proof that it is meant to be aerodynamic. Well done. However, that does not yet tell us if it's meant to be a ball or a weapon, right? What other tests can we do?
Open the inside.
We can cut it open and see what it's made out of. Excellent. We can check the composition. You know what we would find if we cut open a golf ball or whatever this is? What's a golf ball? If we cut that open, we would find an outer layer of plastic. And then you know what's inside? Huh? There's some rubber. And what's basically just foam. That's why it bounces, we find. We cut it open, figure out this is why it bounces. It is full of a less dense material on the inside than it is on the outside. So when I exert force on it, it just barely deforms its shape and bounces upward. It rebounds. So this is a very bouncy object, which is not intended to roll very far, but flies through the air very efficiently. Doesn't exactly sound like the ideal material or shape or form for a weapon. There are far more efficient ways to make a weapon. Therefore, we may safely discount which hypothesis? That it's a weapon. We're therefore left with one hypothesis left, that it is a ball for a sport of some kind. We can then go a level deeper in our examination and our testing and try and play sports with it. It's very effective as a ball for sports, it turns out. You hit it with some things, it flies real far. And then when it lands, it doesn't roll far, right? Therefore, what have we found? We have a working theory that this is, in fact, a ball for a sport. And we have not been able to prove it wrong. It is very effective at that purpose. It was not effective as a weapon. Therefore, we discounted that hypothesis. You following how we do this? This is the progression of the scientific method. Gather the facts. Use the facts to make a hypothesis. Test your hypothesis. Try and prove it wrong. Remember falsification, right? You try and prove your hypothesis wrong the best you can. And when you fail to do so, you have a theory. That theory, that is what you work with until someone else proves it wrong. Okay? That is the scientific method. Questions? Comments? I'm very jangly today. I left my keys on. All right. So, the rock cycle. Brief summary of the rock cycle. You get melted magma. That magma crystallizes into what? Igneous rock. That igneous rock comes to the surface. It gets broken down through what processes? Weathering and erosion transports that weathered material away. It gets deposited somewhere and gets compressed into sedimentary rock. That sedimentary rock gets buried and heated and pressurized through a process we call what? Metamorphism. And that makes what? Metamorphic rock, which again gets buried deeper and deeper until it heats up to the point where things melt and it becomes magma. There's the rock cycle. Well done. Look at that. That was awesome. Okay, now as far as classifying bodies of rock goes, we have some nomenclature here that you should be familiar with because you're probably going to come up against these words at some point during my class and if you are doing your research for discussion boards and other things later on, okay? The first large group, I guess you could say, of rocks, we call that a formation. I will differentiate formations from each other often based on things like fossil content and depositional environment. In this formation, there was an arid desert environment. The formation above it demonstrates a nearshore environment. because they are such different environments, they make different kinds of rocks, and therefore will have different soil fossil contents and chemical content and things like that. And so we draw that line. Hi, camera. What are you doing over there? Whoa, it's freaking out. Come here. Hi, I'm right here. Yes, right here. Was it facing that way the whole time?
Yeah.
Why didn't you tell me anything?
On a tangent, I did it.
Oh my gosh. Okay, well, at least y'all were able to hear what I was saying about the golf balls. You didn't see me write it on the board, but you could hear me as I said it. Okay. Formations, right. Okay, so different layers of rock, we will give different formation names. Now, in a smaller category than formations, we have what are called members. So you can have the Juanita Creek member of the Hell Creek Formation. I just made that up. Hell Creek is a real formation, but I made up the other one, okay? So that's smaller classifications inside of formations. Formations themselves sit within groups, and groups sit within supergroups. Supergroup, right? So I could say that a supergroup represents a series of transgressive and regressive sequences, right? Sea level rose, sea level fell, sea level rose, sea level fell. Okay, so that's within my supergroup. And each group represents a single part of that. So transgressive group, regressive group, transgressive group, right? Inside of our larger supergroup, that includes all of that. And then my formation can be an environment within that transgressive sequence. And my member can be a very distinct period of time that a certain life form was alive during that transgressive sequence, okay? These are all just terms that we use to describe larger and smaller layers of rock that have some form of historical relationship to each other. A sequence, right? You remember we call this stratigraphy, studying the sequence of rocks as they occur to kind of pick apart, and Sherlock Holmes our way to figuring out what the history of that area was. All right, now, do you guys know how big our universe is?
I'd say
Pretty
pretty big.
big. That is accurate. About 14 billion light years across.
I like walk.
You'll light walk?
Yeah, that's like walk.
Good luck. Oh, wow, that was bad. Do you know what a light year is? I need to explain that before that even makes any sense to you. Yeah. What is it? A light year is a distance. Yeah, so it's very confusing to give a measurement of distance a name of time. A light year. Light year is the distance that light travels in one calendar year. Right. Okay. So when I say that a planet or a star is 4 light years away, that means it took 4 years, 4 of our years, for the light from that sun to reach us. Therefore, I am looking at light from that sun 4 years ago. If I were to travel 80 light years away, just like if I could teleport 80 light years away right now and then look at Earth, I'd be looking at Earth 80 years ago. It's pretty crazy, isn't it? For all we know, aliens could be looking at Earth right now. An alien race could be looking at Earth from 65 million light years away, and they don't see us, they see dinosaurs. That's how that would work, because they are just now getting the light from 65 million years ago. That is a huge distance. 14 billion light years? Huge. Within all of those light years are nearly countless clusters of galaxies. And within all those galaxies, millions of stars. And around those stars, planets. We have an estimated, what is that number? Let's see, let's work this out. Hundreds, thousands, millions, billions, trillions, quadrillions, pentillions. 700 pentillion planets in the universe as we can calculate it out. Now, on how many of those planets are there life? Not many, you say. Why?
Because they'd have to be in a Goldilocks zone, like line, or in the range there. You have to have those like specific conditions for life, like the water that.
Okay, so Aaron said something very important. Conditions for life. The Goldilocks zone, you say. The zone around the sun where life can exist. Do you know what that zone is based upon? That original band around the sun that we call the life zone, or the Goldilocks zone, as some people call it. When that was made when our initial belief was you have to have liquid water for life to exist. That's how it happened here. And therefore, that Goldilocks zone is the distance around the sun starting where water, or where ambient temperatures, I should say, are below 100 degrees Celsius and going out to where water can exist at 0 degrees Celsius. Why? What happens at 100 degrees Celsius to water? It boils into steam. What happens at 0 degrees Celsius? It freezes. Therefore, within that zone, you can have liquid water. Earth sits right about in the middle of it. Venus is on this extent. Mars is on that extent. Both just barely outside of that zone. Venus has some water. Mars has some water. Then Venus, it's in a constantly gaseous state. And on Mars, it's in a constantly frozen state. However, we've since broadened our minds to figure out exactly what life could be. Who's to say that life can only exist in the presence of liquid water? That's how it happened here. But some experiments have been conducted that suggest that, in fact, you can form amino acids, which, by the way, are the building blocks of DNA, of protein-based DNA, right? Those building blocks form in the presence of some water to little to no water, but other things, methane, nitrogen, they can still form. When you put UV radiation through methane and nitrogen and ammonia and all this stuff, you form things like adenine, one of the basic building blocks of DNA. There is so much out there that just forms naturally outside of Earth-like conditions that we can see it in space. Okay? One of the building blocks of DNA. Now, is that to say that any life that could exist in a place very different from Earth would look anything like life here does? No, it does not. However, the fact that these building blocks can form outside of Earth-like conditions has caused us to reconsider what the Goldilocks zone is. And once people started thinking like that, they turned to look at other places in our solar system. We'll talk about some of these later on, but I just want to call them out for now. Europa. Europa is a planet made almost entirely out of ice. And Enceladus, a moon of Saturn, also made of ice. But both of these planets are fascinating for a very simple reason. They expel liquid water occasionally in what we call water volcanism. In the same way that Earth is made out of rock and has extremely hot rock in the middle that comes out every now and then in volcanism, Europa and Enceladus have a crust of solid ice, and liquid water is expelled occasionally, presumably because of pressure and heat differences, possibly even convection like we have here on Earth. What is making that water hot? We believe it is because the solid silicate cores of these moons, they're circling massive gas giants, right? We believe that their silicate cores are constantly being pulled and flexed and warped, and that gravitational energy is keeping the core hot and making there be a liquid layer of water inside of these moons. So you've got maybe 15 kilometers of ice and then just liquid water to the core. What could be living in that? These are moons about as old as our solar system, we believe, possibly as old as Earth. What could have developed in that water? Never any light. What's living down there? How fascinating of an idea is that? And now how about Titan? Another moon with an atmosphere made mostly out of ammonia and methane. It has an atmosphere. And atmospheric pressure almost that of Earth. A little bit more, actually. It's about 1.2, I think, or 1.3 Earth atmosphere pressure. I could walk on Titan right now. I feel a little constrictive, like maybe like breathing is a struggle. I'd have to have a breathing apparatus because I can't breathe methane and ammonia, right? It would melt my lungs. But assuming I had that mask, I could walk around because it's got similar gravity. It's got similar atmospheric pressure. I could just walk on the surface of Titan. It has oceans of methane and a crust of solid water ice. And there's something red on Titan. We have no idea what it is. Sorry, no, the red thing is on Europa. The red stuff is on Europa, and we have no idea what it is. We can see it with our telescopes. There are red streaks on the surface of Europa. And we don't know what that red stuff is. Could it possibly be some kind of bacteria? We have red bacteria here. As a matter of fact, we have red cyanobacteria here on Earth that expels methane. Methanogenic cyanobacteria. Could it be something like that on the moon of Europa? And if it was, what does that tell you about the rest of our universe? All of a sudden, we're in a neighborhood. We're not in solitary. Right? Fascinating, fascinating stuff. As a matter of fact, there is a probe being launched to Europa before the end of the decade. They're planning to launch it, and it's going to go to Europa. It's going to take some very close flyby photos. It's going to zoom in as much as it can on this red stuff, and then send its photos back to us. It'll be a long time before we can get anything like a sample back here. But hopefully, we'll be able to tell far better what that red stuff is. Fascinating days ahead, my friends. Our Earth may look unique right now, but we have identified at least 24 other planets using telescopes that appear to have Earth-like conditions. Similar size, rocky body, atmosphere, water, liquid water around stars. The closest one about 4.5 light years away. Right now, if we put all our efforts together, we could conceivably construct a ship that can travel at about 10% the speed of light. Built it in space, launched it in space, did all of that, spent all of our resources on developing this technology. We could conceivably do that. It would take 45 years for that ship to reach this next Earth-like planet. And then 45 years, or if we could transfer at the speed of light, 4.5 years to get that information back to us, right? Those people probably would not come back. They'd be 90 years older if they instantly turned around and came back. And So it would be a one-way trip. But my friends, we're learning so much about our universe. And it's entirely possible that with only a few generations, people could be going out there. I'm working with some people who are very interested in getting people back on the moon. I communicate quite often with individuals, contractors with NASA. They like talking to geologists because any attempt to get back on the moon is going to require geological sciences, because you have to figure out how to interact with the moon's surface. And yeah, mine it. We're going to want to mine the moon. That's a huge endeavor that people are planning to do. The moon is very rich in certain minerals like titanium that Earth is poor in. There are places where we can mine titanium, but they're usually in very hard to reach, inconvenient places. Same thing with aluminum. You remember how we learned about rainforests? We chopped down rainforests for bauxite, that aluminum ore. The moon has tons of aluminum minerals. Mine the moon. I need a big bumper stickers, right? Let's go mine the moon. I had one student a few years back who was really concerned, saying, but if we mine the moon, isn't that going to, like, by removing mass from the moon, isn't that going to throw off its orbit or something? I'm like, you could not possibly remove enough material from the moon to do anything to its orbit. And we could mine the moon for 100,000 years, and we would not be removing enough mass to do anything to the orbit. So who knows? Maybe in 100 years, whatever fleets of colonization ships we have will be made out of materials we got on the moon. Seems like the best case scenario to me. All right. Any questions? No? I'm going to be talking about planetary geology a lot in this class, just warning you. The possibility of life existing in other places, something that I spent a lot of time on. Okay. Well, that's all I got for today. I will not be assigning a lab today. Your first lab will be assigned on Tuesday. Yeah. I'm going to go ahead and end the recording here.